Is it visible?
No, ma'am, it's not visible.
Yes, ma'am. Yes, it is visible, ma'am, please.
Okay, fine. So today I'm going to discuss on machine learning for image computing. So the contents which I'm going to cover today is machine learning techniques, applications of machine learning, on which we are basically going to discuss on image computing, phases of image analytics or image computing, image denoising, image enhancement, image segmentation, image classification. So first of all, I would like to discuss that how could we categorize this machine learning and deep learning and artificial intelligence. So as we know that deep learning is a subset of a machine learning and how machine learning is a subset of artificial intelligence. So I think that this all we know that deep learning is a subset of machine learning, whereas machine learning is a subset of AI. So machine learning, as we know that it has one of the most widely used AI techniques for several companies, institutions, as well as for individuals who are in the business of automation. So this is because of considerable improvements in the access to data and increase in computational power, so which allow us to achieve meaningful results across several areas. So basically, we are using it for predictions or for recommendations basis on the basis of the data. So when to choose the deep learning? So as we know that classical
Dr.
program,
Deepika, the
yeah,
slides are not moving, madam, actually.
slides are not moving.
Now there.
Let me share
Yes.
it again.
Please.
Is it visible?
Yes, madam, it is visible.
Is it moving now?
Yes, yes, ma'am, it is moving.
Do I go to the mode?
Better
Is
to
it
go
okay?
to. This is also okay, madam. The slides are visible, please.
No, it's moving also.
Now we can see this AI, ML, and deep learning slide.
So I'm switching the slides. Is it not switching?
No, no, we can only see if the one slide only. It is not switching now.
See the switching.
Better you share the entire screen and go. Then that will be better.
Yeah, I have shared it. On slideshow mode, I think that it's creating some issue.
I think you can reshare the screen and share the entire screen. That will be a better option, madam. Then.
Yeah, I have shared the entire screen. Could I share it through the browse my computer or just I could share my screen?
Better to share you the entire screen, madam. The first option that will work.
Okay, entire screen. Right. Now is it possible?
Now the screen is visible, madam. Can you just move the slide so that we'll see? Now it is visible.
Yes,
First
ma'am.
slide.
Yes, ma'am.
Yes, yes,
Okay, okay, fine.
yes, yes, please.
Okay, so here I was discussing about the difference between classical programming and deep learning. So where we are choosing the classical programming when we have a rules which are clearly defined to us, straightforward, then it's better to just program it. But if the rules are nuanced, complex, and difficult to discern, then use the deep learning. So here we know that the number of techniques in machine learning, which is like your supervised learning, unsupervised learning, semi-supervised learning, and reinforcement learning. So here we can see that uh, in supervised learning, what we have, when we have a labeled data with us, it means that we can provide a training to a machine to perform that particular task. And in unsupervised learning, we can use these algorithms when we don't have a label data. Like if I want to cluster some emails, that what are the spam emails. So there we can use a clustering. So here our data is not labeled, but on the uh, basis of there some characteristics, we are categorizing the data into different groups. Then we have a semi-supervised learning algorithm, which you can see that it is a hybrid combination of supervised techniques and unsupervised techniques. For example, the Facebook, when we upload the when we are going to upload some image on a Facebook and we are giving the tag to one image, then it is we have trained the machine that this image is of this particular person, and automatically whenever that image of that person is uploading in any images, it will automatically tag those images that this is a person A in this image. So that is a semi-supervised learning algorithm, which is used by Google Photos or Facebook. Another technique we have a reinforcement learning. Here we don't have any data. We can say that it don't we have any label data or label data. But here the reinforcement learning trained, or you can say that it can perform according to the current status, and according to that action which it is going to take, the penalties or rewards would be given. So we are basically using these reinforcement algorithms in gaming, etc. So then we have a subset of machine learning where we are using neural networks. So which is like CNN, DNN, RNN, autoencoders, and MLP. So these are the various categories of machine learning which we are using in our image processing. So these are some open data sets which are available, and you people can explore it from these links which are given here. So these are the techniques which I have just discussed with you, that what are supervised learning and unsupervised learning. In unsupervised learning, we have a SOM, autoencoders, RBM. Then in supervised, we have CNN, RNN, LSTM, and GCM. So here we have shown some difference between machine learning and deep learning on some parameters. What are those parameters? The basic difference between machine learning and deep learning is that in machine learning, we are extracting the features manually by using some feature extraction and selection algorithms. Whereas in deep learning, there is no need to extract the features manually. Okay, it is doing everything on its own. We are just providing the data, and on the basis of that data, it trained itself. So the parameters on which we can distinguish both this machine learning and deep learning are like data dependency. In machine learning, if you have a less amount of data, machine learning can work because here we are extracting the features manually. So if you have a less images like 200 images or 300 images, your learning model will work. But if you have a 200 or 300 images and you are applying the deep learning on that model for object recognition, like you want to recognize whether this image is a car or not a car. And if you have a less amount of data, then there may be a chances that you are not providing a training in a good way, accuracy couldn't be better. So in deep learning, you need a large amount of data. So whenever we are facing a problem of less data, what we do augmentation so that we can increase the amount of data. Second parameter which we are taking is execution time. So machine learning takes less time. As I told you that we can train our model with less data, but here in deep learning, we need large amount of data. So quite obviously execution time would be more. Hardware dependencies, as we know that images are like it occupies a lot of spaces. So when we are providing training with images, again, we need a good hardware. Okay, so that's why we are today working on GPUs. We are working on GPUs. Okay, then feature engineering, again, deep learning is doing feature engineering automatically. Problem solving approaches, again, depends upon that what type of problem for we have a problem, what type of problem we have for which we want to use machine learning or deep learning. So these are some basic parameters on which we can distinguish the deep learning and machine learning algorithm. So these are some frameworks which are generally popular, and image processing and computer vision problems are generally, we are working with these frameworks which are Keras, TensorFlow, Theano, Caffe, Torch, Caffe2, Deep Learning 4J, MXNet, Microsoft Cognitive Toolkit, Channel. So you people can explore these links. So here are we can see the number of applications of machine learning, but today we are going to focus only on image analytics. So what is image? As we know that a picture is worth 1,000 words. So picture is a two-dimensional matrix. You can see here. So it depends upon that your image is 2D, 3D, multi-dimensional D, 4D, 5D, whatever dimensions there. But basically, if on the basic grounds we want to see that how image is represented is in the form of a 2D matrix. 2D matrix means that we have some rows and columns. And each rows and columns, these are known as some special coordinates, which are represented by some pixel like 0, 1, 2, 3, 4. These are the pixel values. So here we are again talking about the 2D image, which means two-dimensional. Two-dimensional means we have a rows and columns. So our image is actually stored in this form of a two-dimensional matrix, or you can say array. And how these pixels are stored? These pixels are stored in the form of a one vector, 1D vector. You can see here 0, 1, 2, 3, 4, 5, 6. So these images looks like these pixels in the form of two-dimensional matrix, and these pixels are stored in the form of a one-dimensional vector. So if I'm talking about a binary image, it means that we have a 2 bits, that is 0 and 1. And if I'm talking about a gray level image, it means that we have a 8 bits. It means 2 raised to power 8, which has a range between 0 to 255. You can say that it has a 256 pixel values. And if I'm talking about the colored images, it means that it is a red, green, blue, which means 2 raised to power 3 means RGB image consists of 24 bits. So here you can see the image, this particular block we have represented in form of this array. So this particular cat, we can see this cat, but computer is not able to understand that image. The computer understands this. What the computer sees? The computer sees this two-dimensional array in which we have some numbers. So again, if it is a grayscale image, it will represent the pixel values between 0 to 255. And if it is RGB image, then it will represent each pixel value as a red channel, green channel, or blue channel. So this is an image. Now the methods which we are using to perform some operations on an image is known as image processing. So why we are doing this processing of an image is sometimes we want to enhance the details of an image. Then we are processing the images in order to enhance or improve the quality of an image. Or sometimes we need some useful information from that image. To extract some useful information from that image, like we are performing segmentation. Sometimes we want to recognize something in an image. Sometimes we want to extract something. Sometimes we want to predict something. So all these operations when we are performing on images, then it is your image processing or image computing. So it is a type of signal processing in which input is an image and the output may be an image or characteristics or features associated with it. that image. So today, when it comes to image data, machine learning algorithms can interpret images the same way as our brains do. These are used almost everywhere, right from the face recognition while capturing images on our smartphones, automating tedious manual works, self-driving cars, and everything in between. So here our computer vision comes. So it is a field of computer science that works on enabling our computers to see, identify, and process the images in order to recognize different objects. So here we are going to make a deep diving into the machine learning image processing fundamentals, and we are going to discuss various technologies that we could leverage to build the state of the art algorithms on the image data. So these are machine learning frameworks and image processing platforms: TensorFlow, PyTorch, MATLAB, Microsoft Computer Vision, Google Cloud Vision, and Google Collaborative. So as I told you that image processing is a computer technology which we are applied to the images that help us process, analyze, and extract the useful information from them. So it is among rapidly growing technologies and has evolved widely over the years. So like these image processing algorithms are using by different organizations of different sectors for various applications such as visualization, image information extraction, pattern recognition, classification, segmentation, and many more. So these are some neural networks for image processing. As I told you that we are going to make a deep dive on these images. So before going to discuss about these neural networks for image processing, I would like to discuss that where we are applying this image processing in medical imaging or visualization, where we can help the medical professionals to interpret the medical imaging and diagnosing the anomalies. We can also apply these image processing algorithms in law enforcement and security, which will aid in surveillance and biometric authentication. It is also using in self-driving technology, which assists in detecting the objects and mimicking the human visual cues and interactions. Yes, we can also use this image processing in gaming, which will help in improving the augmented reality and virtual reality gaming experiences. And we are also using it in image restoration and sharpening, where we can improve the quality of images or add the popular filters to it. And we are also using it in pattern recognition, where we are classifying and recognizing the objects in images and understand the contextual information. And at the last, we are using it in image retrieval also. So you can see that today we can search anything, we can search from the images in Google search through, we can search from images. So that is the image retrieval, where we are recognizing the images for faster retrieval from the large data sets. So this is, as I told you, that we are working with neural networks for image processing. So machine learning algorithms have a specific pipelines of steps to learn from the data. So let's take a generic example of the same and a model of working algorithm for image processing use case. Firstly, machine learning algorithms need a considerable amount of high quality data to learn and predict the high accurate results, right? So we will have to make sure the images are well processed, annotated, and generic for machine learning image processing. So this is where computer vision comes into the picture, and it is a field concerning machines being able to understand the image data. So using computer vision, we can process, load, transform, and manipulate images for building an ideal data set for the machine learning algorithms. For example, say we want to build an algorithm that will predict if a given image has a dog or a cat. So for this, we will need to collect images of dogs and cats and pre-process them using the computer vision. So what will be the steps for that? The pre-processing steps will include converting all the images into the same format. Okay. Then cropping the unnecessary regions of the images and transforming them into the number for algorithms to learn from them. So computers see an input image as an array of pixels, and it depends on the image resolution. And based on the image resolution, it will see height, width, and dimension. Okay, so these features are then used in the next phase to choose and build a machine learning algorithm to classify unknown feature vectors given an extensive database of feature vectors whose classifications are known. For this, we will need to choose an ideal algorithm. Some of the most popular ones, like as we can see that Bayesian nets are there, decision trees are there, genetic algorithms are there, nearest neighbors, neural nets, and deep learning, we have a CNN, NASCAR CNN, fully convolutional networks, and UNet. Generative adversarial networks are also there. So these are some tools for image processing. So these are the various applications of image processing. So this is a CNN, which I've just discussed with you that what are the steps actually we use. So CNN is a very popular technique, or you can say it is a very popular model which everyone is using on image processing or image recognition. Right? So CNN is basically consisting of four steps, which is convolution, max pooling, flattening, and full precision. So here what we are using convolution. So we all know that what is a convolution? When we are convolving the filter to a subimage. Right. So that is the convolution process. And after that convolution, whatever we are getting the features, we are making pooling of it because we are doing a feature reduction. So again, it depends upon that what type of pooling are using, max pooling or average pooling. But generally, we are using the max pooling. After max pooling, we are doing flattening, and then we are making a fully connection. So here we are using a multi-classifier. We are classifying the dogs, cats, lion, and birds. So these are different CNN architectures. Like in 2000, in 1998, we have a DayNet. Then in 2012, we have a AlexNet. In 2013, we have a ZFNet. In 2014, we have a GoogleNet. In 2014, we have a BGGNet. And in 2015, we have a ResNet. So what is basically the difference between various CNN? This is the difference between the architecture, the difference between the architectures of CNN and the difference between the layers, like how many layers and what is the base architecture, what is the backbone of this particular architecture. So there are slight differences between each architecture of CNN. So we can also make a new architecture by studying all these basic concepts of basic architectures of CNN. What is the basic architecture of CNN? Then what is the basic difference between ResNet 16, BGG 16, BGG models, AlexNet models, ResNet models. So there are some basic differences in the architecture. So if one can understand the basics of these architectures, then architecture by analyzing all these things. Then if we are going to use any model, any CNN model for our image processing, we need to understand that how could we tune these parameters. Like as we have discussed here in CNN, as I told you that CNN, in this CNN we have a convolutional layer, which is the heart of the CNN. It does most of the work in identifying the features in the given image. Then in the convolution layer, we consider square blocks of random size of the input image and apply the dot product to the filter. If the two matrices have high values in the same position, the convolution layer outputs will be high. And if they don't, it will be low. So in this way, a single value of the output of the dot product can tell us whether the pixel pattern in the underlying image matches the pixel pattern expressed by a filter. So you can, if you don't know about convolution, you can Google it also. So after convolution, we have a pooling. When we identify the feature using the convolution layer, we have multiple feature maps. So you can see here that we are having multiple feature maps, which results when the convolution operation is applied between the input image and the filter. So we need one more operation which downsamples the image. So To make the learning process easy for the network, the pixel values in the arrays are reduced by using the pooling operation. So they operate autonomously on every depth slice of the input and resize it spatially. This is our pooling. And fully connected layer means it operates on a flattened input where each input is connected to all the neurons. So when we are using all these steps in CNN, we need hyperparameters. And it is very important to use these hyperparameters, which are learning rate, path size, momentum, data and stopping criteria. So if we tune these parameters appropriately, then our model will definitely give good results in terms of accuracy. But if you are not selecting these hyperparameters in an efficient way, then you would not get the good accuracy. So it's very important to select to tune these parameters. These parameters are related to the training process. Okay. Am I audible?
Now you're audible, madam. Just we lost you just before 1 minute.
Am I audible? Hello?
You're audible, madam, please.
Is my screen visible? Hello?
Yes, madam, your screen is visible.
Okay, fine. So this is various steps of image processing where we have image acquisition, pre-processing, segmentation, feature extraction, selection, and then classification. So these are various processing operations which we have applied on an image. The images which we are taking here, which you can see on this slide, is histopathological images of the breast cancer. So the main challenges of applying these machine learning or deep learning, or you can say artificial intelligence, to medical images or for cancer diagnosis is the lack of data, because we don't have so much data. So this is one of the problem. Issues of data access and integrity, and the black box problem. So these are the three challenges which we are facing. So the first challenge, which I told you, that lack of the data. For that problem, what we do generally, we do image augmentation. In image augmentation, we apply different types of operations like flip the image, crop the image, blur the image, contrast the image. So these are some small operations which we are applying on in images so that we can extend the data set of an image for providing the better training to our model. These are a different augmentation techniques. Another one is another issue which I have told is the black box problem. So this black box problem is handled by our we can say that extendable AI. Whatever I do, when I said that I'm going to classify the cat and dog images, my model will tell me it is a cat, it is a dog. But how it is going to tell me that it is a cat, it is a dog? So this kind of explanation is missing. So that's why we are saying that our machine learning models are black box models, because it gives answer to us, but it fails to explain that why the model has given this particular answer. So there's a lot of work is going on in XAI, explainable machine, or explainable machine, so that we can explain with our model that why the answer is there, right? So this issue is also a lot of work is going on explainable also. Then another operation is image denoising. In image denoising, we have different types of techniques like autoencoders, relative adversarial networks, residual encoder decoder networks, multi wavelength sequence, beloved real image denoising networks. Machine learning models which we are applying on see image denoising. I have seen that a lot of people getting confused between image denoising and image enhancement. Image denoising, as the name is telling, that denoising, we are removing the noises from an image, and it depends that what type of noise is there in an image. Now it depends upon image. If I'm taking a general natural image, it may be corrupted from a Gaussian noise, white additive Gaussian noise. If I'm talking about the ultrasound image, then ultrasound image is corrupted from the speckle noise, sound signals, unnecessary sound signals. So that type of noise is multiplicative noise. But if I'm talking about additive white Gaussian noise, then that noise is a additive noise. So there are two types of noises, additive noise and multiplicative noise. Now, it depends upon our image and from where we are recording that image, whether that image is corrupted from the additive noise or multiplicative noise. So we need to use the probability density functions to model, to simulate that particular type of noises. So these are the general models which I have gone through the papers which are working on the additive noise, but till date I haven't found any model which have worked on the multiplicative noises. It has worked on the additive noise. So this is again a new uh, work researchers are removing. Can you please mute your mic?
Yes, madam, please proceed, please.
For denoising images, again we have different types of evaluation criteria or subjective criteria, where we can visualize our image that yes, it is a clear image, there is no noise. Or if there is a noise, then we can say very poor, poor, good. So this is a subjective evaluation. Another evaluation is objective or quantitative, where we can calculate some mathematical value like signal to noise ratio, mean square error, signal noise ratio, root mean square error, structure similarity index, or edge preserving index. So these are some quantitative evaluations which we perform. So this is one sample uh, which I have shown here for your understanding. Like you can see here, this one is the original image. This one is an original image. Okay, and here original image means noisy image, and this is the result. This rednet image. This is a pretnet, and this is the MWCNN. So here we, if I want to make a subjective evaluation, I can say that this is performing good. Pretnet is performing good. This is okay. This is poor. This is subjective evaluation. But if I'm calculating the PSNR, I'm calculating the pretnet, I'm calculating the value of MWCNN, SSIM. So this is my objective evaluation where I'm taking some values. So I have also seen in some papers, as I reviewed some papers, what people don't have a ground truth image. Okay, ground truth image means that a clear image. This is my noisy image. Okay, so what like a clear image where we don't have noise. If you want to calculate PSNR, SSIM, you must have a clean image without noise. Okay, and then we can simulate that clean image with different variances of noise, like 0.5, 0.7, 0.8. So you have one clean image, you have a noisy image, okay, and then you are applying your model. This is your resultant image, okay. So when we are going to calculate the PSNR, I need to it two images. What I'm audible?
Yes, madam. You're audible, please.
Okay, so this is what we have image denoising. Then in image enhancement, as I told you that in image denoising, we are removing the noise. But in image enhancement, we are improving the quality of an image. Like if the contrast is not good or brightness is not good, then we are improving the quality. So this is the basic difference between image enhancement and an image denoising. We have number of techniques for image enhancement also in machine learning, like image super resolution enhancement, image restoration, repair and painting, image dehazing. Again, lot of work is going on this image enhancement using super resolution or in image restoration or in image dehazing. So this is image resolution. You can see that we have enhanced the image with the help of super resolution algorithm. Image repair in painting, sometimes what we have folded image or something is missing from an image. Then we have number of techniques for repairing those images or for in painting. So you can see in this image also. Then in image dehazing, where we have a lot of dehazed image, we have a lot of hazy images. You can see here, this is a forest scene with the hazy image. With the help of dehazing algorithm, we can dehaze the image. So you can see here in the right image, we have a more enhanced clear image. So another operation is image segmentation. Again, image segmentation can be applied on image medical imaging in locating tumors, studying the anatomy, in self-driving cars, or in satellite image interpretation. So these are number of deep learning based image segmentation algorithms, FCNN, multi-scale, RCNN, recurrent neural networks. So generally we categorize these techniques into semantic and instance segmentation. So here you can see these pink blocks are referred to as semantic algorithms, whereas these green are your instance segmentation algorithm. In instance, actually, what's the difference between semantic and instance segmentation? In semantic, suppose we have some cats and dogs in an image, then semantic, what will do? It will color all the cats in a blue color and all the dogs in a yellow color. Okay, it will divide it into two blocks. But in instance segmentation, what it will do, if there are three cats, it will give ID to each cat. It is ID1 cat, ID2 cat, ID3 cat, ID4 dog, ID5 dog, ID6 dog. So it will provide individual tag, individual ID to each object in instance segmentation. So a lot of work is going on in instance segmentation nowadays. So this is again a very good topic where students can work on this instance segmentation to explore this area also. So these are number of techniques on which number of people are working since 2014. So this I have only up till 2019. After 2022, there are a lot of techniques. So this is what I have told you, that in object localization, we are providing a bounding box. And in semantic segmentation, this is semantic segmentation where we have just colored the objects. But in star segmentation, we have provided different colors to each object with different IDs. So this is the difference between the star segmentation and semantic. So these are different evaluation metrics for segmentation. Again, for any technique, we need how we can evaluate the performance of algorithms. So again, we have to positive, false, positive, true negative, false negative, accuracy, overlap metric, cost of distance, similarity index, Jaccard metric, misclassification error. On the basis of this, we can evaluate the performance of our segmentation algorithms. Then we have a classification where we are classify the images like whether it is a bird, sunset, dog, or cat. So for classification, we have different evaluation metrics. Again, we have a confusion matrix, precision, recall, sensitivity, specificity, even score, AUC, ROC curve. So this is a difference between detection, classification, and recognition. This is explainable machine learning, which I have told you that our models are working like a black box model, because it won't be able to explain that why the model has given this result. Like if my machine learning model says that it is a cat, okay, so what is the current explanation of this, that why the model has said that it is a cat? Because it has a fur, whiskers, and claws, and it has these features. That why uh, our machine learning model has says that this is a cat. So there are number of explainable XAI techniques. There are number of explainable machine learning models like SHAP models and etc. Number of models are there for explainability. So you can also explore those explainable machine learning models. Then another operation is image fusion. Image fusion means that where we are overlapping the two images, and then we are getting one image. So this is one big, you can see this is a near focused, means the front object is clear, but the far object behind this object, it is a blur. The background is blur. And in the second image, you can see the front object is blur, but the background image is clear. So what we are doing, instead of storing these two images on our computer because it will occupy the space, we will overlap these two images and we'll get this fused focused image. So this is a function of image fusion, and there are number of types of image fusion like multimodal, multifocus, multi-sensor image fusion. So this is an example of a multimodal where we have fused the MRI and FDG image. So this is the results of one of our paper. Then image retrieval, as I told you that we are using today images as a query and then we are retrieving the images. This is one of the another operation. These are the operations which I mentioned in the content. Then image to image translation. This is again one of the area where the people are working that how could we translate image to image. Image captioning, where we are providing captions to an image. Image encryption and steganography is another area where here you can see this red box is our carrier image to hide our secret image, and blue box is the secret image which we want to hide, and the green box is the carrier image after hiding the secret image, and purple box is reconstructed secret image from the green box images. So in the image encryption steganography also number of work is going on. Then image forgery detection is again one of the popular area. These are the number of algorithms for forgery images on which people are working. This is again an image watermarking where we can remove and detect the images. This is deep dreaming where we can make number of arts with the machines.
Ma'am, it's not audible, ma'am. Deepika, ma'am, the voice is not audible, ma'am.
Am I audible now? Hello?
It's audible, ma'am. It's audible. It's audible, ma'am.
Okay, okay. So these, since when my voice is not audible? So these are the number of image analysis techniques where we can apply the images. This is all. Thank you. Please ask some if you have any question. I think my voice is not audible to you people.
You're audible, madam. You're audible.
Okay, fine. So this is all about from my side. If you have any question, please ask.
Any queries, please? Kiran sir, can I continue?
Yes, madam. Yes, please.
Thank you so much, ma'am. Thank you so much, Dr. Deepika Koundal, ma'am, for such an adorable presentation on machine learning for image computing. Thank you so much for your valuable insights, ma'am. Thank you so much.
Thank you, ma'am. Thank you, sir.
Ma'am, can we have your PPTs?
Yeah, sure. I'll share.
Thank you, ma'am.
Thank you very much, Dr. Deepika. Have a nice day.
Thank you so much.
Good evening for all the